0.1 microseconds to occur. What is 0.1 as a decimal? Or fraction?
1/10.
1/10.
10.
Where is this going?
Over what?
Oh, you're period. So what are we dealing with? 10 what?
Megahertz.
Mega.
Reciprocal.
So I can trip over the block. That'll learn. Do without touching. Yes. Yes. Please. Yes. Okay. So next up, what is the wavelength of this in soft tissue? So wavelength equals C over F. What are we using as our constant for C?
1.54.
1.54, right? Divided by. So our wavelength equals. And what's our unit?
Millimeters.
Okay. Okay. So now we're going to go to that chart. So help me with the chart. Okay, what's on top?
She likes her noises too. Yeah. Time.
Time. What's on the bottom?
Distance.
Distance. And so we have a 2 megahertz wave, so that's 2 megahertz. And then we have 4 cycles. So let's draw our 4 cycles. 1, 2, 3, 4. Okay, that's there. So how do we find out pulse duration? What's our equation for pulse duration?
Period times number of cycles.
Period times my number of cycles, right?
Yep.
So in this case, we have our number of cycles is 4. We have to find our period. How are we going to find our period?
From our frequency.
So period equals 1 over F. We've got our frequency of 2, so period equals 1 over 2. What is that as a decimal? Please tell me you know this.
0.5.
Yes, so 0.5. So our period is 0.5 what? Microseconds. So we're going to take our 0.5 times 4, and what does that give us? 2 what?
Microseconds.
Microseconds. How are we feeling about this? We want to do it again?
No, it's too easy.
Too easy! Oh!
We're not all in the same boat as you, Tanya. But I know I can sit beside you in the exam.
So what is our duty factor? What's our equation for duty factor?
Pulse duration over PR.
Times 100. So we have some of this. Pulse duration. Oh. We have 2 microseconds. Now we have to find our PRP. So what is our equation for PRP?
F.
PRP equals 13 somethings.
You said
13 wheelbarrows. Okay. Times
that.
centimeters. And where we're at?
10.
10. So times 10. So what does that give us?
130 cents.
So we're going to plug in Mr. 130 down here. Oh, look, I'm doing all this math.
1.5.
2 divided by 130 equals 0.015, and then we're going to multiply that by 100. So duty factor equals, we run our 100 in there, 1.5%. What's that one for you? Yes.
And that would be a large duty factor.
Yeah, yeah, because, yeah, in the real world, yeah. We're just playing.
Yes.
Trying to make it the best.
Mhm.
Okay, so in your little brains, cute little heads, so help me out with this chart. Okay, so for time, the time of one wave.
Period.
One wave to occur.
Period.
Period. How about my whole thing? My whole
Wavelength.
Pulse duration.
pulse duration. What's my equation for pulse duration?
Periods times cycles.
Times cycles. And then what about this guy down here? Distance. The distance of one wave. The length of one wave.
Wavelength.
Lambda.
The length of one wave.
Lambda.
Wavelength,
Yeah.
you're right, you got it. Okay, so how about this bad boy? Our pulse in space. The length of our pulse in space.
Spatial pulse.
Spatial pulse length. So what's the equation for a spatial pulse length?
Wavelength times number of cycles.
You got it. Now there's a couple more equations we can add to this. So there's one that's off the chart, but he's kind of related to the on and off time. So that's our PRP. And we decided his equation was what?
1 over, oh yeah.
Times number of centimeters depth. And then we also had, well, let's go duty factor first. We just worked with duty factor. So that's our, how much work we're doing. So our on time with our off time, the percentage of on time to off time. So that's going to be our pulse duration over pulse repetition period. And then down here, we had our spatial pulse length. We haven't talked a ton about this. We touched on it a little bit. We're going to get a whole lecture on it, but it's that axial resolution. So what is axial resolution dependent upon?
SPL over 2.
Divided by 2. You got it. And we'll talk more about that in a lecture later on. But that's our, our resolution down our beam this way. We've talked a lot about the hourglass thing, but this is actually down the beam, whereas our hourglass is going to be across the beam. So this is what we call lateral resolution, and this is our axial resolution. And there's other words for these, you know, the same, like we call it lateral. There's a bunch of different words that mean axial resolution, and a bunch of different words that mean lateral resolution. We'll talk about that later. So, how are we feeling about the chart? So it's not just memorizing, it's being able to put it together, right? Here's one wave, here's the time, here's the distance, here's a pulse, here's the time, here's the distance. What can I do with those numbers? Well, I can determine my duty factor, or I can determine my axial resolution. Then if I know my depth, I can determine my distance. Cool so far? Questions so far? Okay, so today we're going to talk about, let's go back a little bit. We talked about a single wave. We talked about if we have more than one wave, so it's these guys, right, the chart. Now we're going to talk about, okay, we have these waves going into our patient's body. When we talked about that word attenuation, remember how our beam decreases in volume or decreases in amplitude as it's in the body and reflects back? So what happens to it? So what we're going to talk about today is what happens to it. So our attenuation. So attenuation is measured in logarithms, so basically powers of 10. Do you really need to know this? No. There's a few that you need to memorize, but they're not going to ask you anything that's outer spacey about, oh, you have a log of 0.5, like I don't know what that means. So we'll talk about some logs that are a little bit more constant, which are these ones. So you'll need to know these ones. If I increase by 3 decibels, I'm taking that numeric value and doubling it. If I increase by 10 decibels, I'm taking that numeric value and multiplying it by 10. Conversely, if I attenuate, I decrease in amplitude by 3 decibels, I'm going to halve that intensity. If I have a decrease of 10 decibels, I'm going to take that intensity, that amplitude, and I'm going to divide it by 10. So these are the ones that you're going to need to memorize. Whenever we talk about attenuation, we always talk about it being a negative, because our beam is going away. So it's going to attenuate by 3 decibels. That doesn't mean it increases, that means it decreases by 3 decibels. So attenuation always implies a negative. These are the ones that you're going to have under SPI, and they're going to be most common because they're the easiest ones to do now. It's either divided by 2, or multiplied by 2, or it's divided by 10, or multiplied by 10. So those are the 4 that you're going to need to memorize. Okay, so attenuation. So as our beam goes into the body, it's coming out at a certain amplitude or a certain volume, and as it goes into those tissues, it's going to decrease in volume. And there's 2 ways that it decreases. We can talk about it, how it applies to frequency. Remember how we love those high frequencies because they have really good resolution, but they don't penetrate very well. So I might be able to look at the thyroid with a 10 megahertz, but if I'm looking at the liver with a 10 megahertz, I'm not going to be able to see all the way through. It attenuates. So remember those rarefactions and compressions? So if I look at, let's go back here to the report. This is my workout. Oh man, okay. So this is like, years ago I was watching this teaching video. They were talking about teaching, and they were talking about like, when you do the whiteboard, that's like a teaching method, like make it like a real, like instruction method. Okay, whatever. Okay, done. I'll show you.
It's so funny.
Okay, so if we look at a high frequency and a low frequency, so here's our long low, these are short high. So every time this moves through the tissues, it has a rarefaction and compression. So if I'm going the same depth, this has maybe a much larger spread of rarefaction and compression, whereas this is going to have a lot of rarefactions and compressions in this goes. We're just going to make up the depth. So the more rarefactions and compressions that a wave has, the more it attenuates. The less rarefactions and compressions a wave has, the less it attenuates. So that's why we can use these lower frequencies to penetrate deeper into the body, because they have less rarefactions and compressions. And we'll talk about the ways that our beam attenuates, but we're going to have less of those rarefactions and compressions, and less of our beam is going to attenuate. We have better resolution here, and we'll talk about that with that axial resolution stuff later on. We have better resolution, but less penetration. With this, we have improved penetration, poor resolution. So that's kind of the trade-off we have. So we can talk about attenuation as it applies to frequency, and then we can also talk about it as it applies to depth or time in the body. So remember those TGCs, time gain compensation? So when you're doing that left liver lobe, that bottom field isn't very dark, is it? We're not in the body very far. Our beam comes back at a relatively high amplitude. But as we go to that right liver lobe and we add that depth, our beams in the tissue is a lot longer. It's going a lot deeper, and so it's going to attenuate more. We're just going to see more rarefactions and compressions. So versus 10 centimeters versus 20 centimeters. So I'm going to have more rarefactions and compressions as we go to that more depth. So we're going to lose more of our beam the deeper we go. And that's like your neighbor has some lady stuck in the basement, and she's yelling for help. If you're close, you're going to hear her. But if you're far away, that is going to attenuate, and you're not going to hear her very well. Makes sense, right? Mm-hmm. One other thing, you know when it's snowy out, it's really quiet? That's because the sound is attenuating off of all the snowflakes. That's why it's so quiet when it snows.
I didn't catch it.
Okay. So how do we lose this beam? How does our beam actually attenuate? How do we have those rarefactions and compressions, but what's happening during that that's changing our beam? One of them is reflection, one of them is scattering, absorption, and then refraction. Now there's rarefaction, refraction, and reflection. So don't confuse them, they're totally different things. But your book doesn't think refraction is a very big deal, but it is. Remember that edge artifact we talked about, where I have my beam is coming in here, kind of bouncing off the side, so I get the shadowing here? That's a form of refraction. We're going to talk more about that in our PowerPoint later. But our book is like, yeah, refraction, big deal, but it is a big deal. Your book kind of skims over it. Okay, so when we talk about reflection, there's a few different types we can talk about. And these are going to apply to the type of tissue boundary and how big it is in relation to our wavelength. Whether it's much larger and flatter than our wavelength, whether it's about the same as our wavelength, or whether it's really tiny compared to our wavelength. So that's going to create different types of scattering, or reflection, I should say. Let's look at these guys. So specular reflection. This is the diaphragm. We have this big, or when you look at the aorta, and it has those nice straight walls, and they're very bright. So our beam is coming in, and it's reflecting off like a mirror. It's a big flat sheet. So things like diaphragm, that aortic wall, that gallbladder wall, that anterior gallbladder wall that's nice and bright. So we have our beam coming in here. Some of it's going to transmit through, and then some of it's going to come right back to our transducer. So it's a nice flat boundary. So we're getting a lot of reflected beam back. A high amplitude of beam is reflected back. So a significant amount of volume is coming back to our transducer. Now there is one oddball thing that can happen. So say we're angled somewhere like this and our beam is coming in. We can have what's called, oh you're good, critical angle, or what we call internal reflection. And so it's hitting off of this flat sheet, but it's going out into the body so it never returns to our transducer. So that can happen as well. And when you're scanning like that, you'll just notice like, hey, everything's flat. Okay, just move a little bit and it goes back to the wheel. So it's a very near, like very flat. So this is our specular. Let's really note over there. So specular. It's flat. Just like Shea in high school. Don't even know. So there's that one. And then there's diffuse, which is also called backscatter. And what this is this going to be maybe slightly larger or even with our wavelength. So we've got this tissue boundary that's maybe looking something like this. Oops, my pen decided. And so here's my beam coming in. So some of it's going to come in and go straight back to my transducer. Some of it might bounce out of here a little bit. And so it's coming back. So if I have, kind of the amplitude that's coming in, some of it's going to get lost in the body. So I'm still getting some of it returned back to the transducer, but I'm losing some of it. So it's attenuating. I'm losing some of that beam. It's being kind of scattered around. We do get a lot of beams back from this because it's such a large interface. So this is going to be according to our wavelength. So it's going to be either equal to or just maybe slightly larger than, or just slightly larger than our wavelength. Equal to or just slightly larger than our wavelength. So we get a lot of beams reflected back, but we're still attenuating. And that just happens. Attenuation just happens. It's a property of physics. We can't do anything about it. Like what's your attenuation coefficient? Like, I don't know. What is, I don't know. Who knows? So nothing you're ever going to be asked about except on the SPI. So next up, we have scattering.
Yeah.
Okay.
Gloves. I don't know. I think janitor.
Oh. Sorry.
Okay. Yeah.
Bless
Oh.
you.
No, you're fine. So our paper towels back here. Okay, thank you. Okay, so next up we have scattering. So this is going to be equal to or much smaller than our wavelength. Hopefully it's still the same. Okay, so what am I talking about? What was the one?
It was diffuse.
Diffuse. Thank you. So that's going to be, maybe a little bit larger or equal to our wavelength. Then we have scattering. No problem, take your time. We're no hurry. They're teaching, I'm learning physics, so they don't want to learn any more than that. Okay, so this is where our beam comes in. This is what I think of as kind of a disco ball. So like if I look at a mirror, right? And then I look at like small pieces of mirror, some of my reflections coming back, and then like a disco ball, like it's being scattered everywhere, right? It's really tiny, tiny little pieces of kind of reflection. And so as our beam comes in, some of it's going to come back to us, but a lot of it is going to get kind of scattered around different places. So this is going to be very small compared to our wavelength. And there's one of these that you guys have seen and you didn't even know it. So when you were scanning that IBC, did you see some kind of gray wispies going by? Mm-hmm. Yep. So that's called Rayleigh scattering. And that's a very special kind. And these are where they're super duper duper tiny compared to our wavelength. Very small. Small. It's my name small. I know I smell small. But very small. So that's what we have. We see this with red blood cells. We have all these little blood cells cruising around in this vessel. And so some of our beam is going to go through this and just continue on and image for us. Some of it's going to come back to the transducer from these little tiny little red blood cells. And some of it's going to get scattered away. But Rayleigh scattering is they're very, very, very small compared to our wavelength. So not just like the scattering where they're smaller than our wavelength, but extremely smaller than our wavelength. And we can see this most commonly in the IBC when you see those little wispies. When you guys start looking at urinary bladders, you'll see some of the urine sometimes in there. If there's a little bit of debris, you'll see some of that kind of swim around in there as well. Yeah.
I feel like I get the types of textures that go with these different ones, but can you go over the wavelength again, like how they compare in size to the wavelength of our beam?
To our wavelength?
Yeah.
Okay. So first up, we have specular. These can be very
smooth, flat. Yeah.
Yep, so our beam goes in, it comes straight back out.
And it's larger than our wavelength?
Much larger.
Okay.
Much larger, yeah. So
and it goes down.
Larger than wavelength.
Yeah. And then diffuse would be kind of wavy.
Kind of wavy, yeah. So diffuse is more like this.
Irregular.
And so it's going to be larger or somewhat equal to, we'll do, to our wavelength.
Gotcha.
And then so we get some of this is going to come in and come back, and some of it's going to actually boop.
Okay.
So we're just not getting as much back.
Yeah.
So these are these are decreasing intensities as we go.
Yeah. Okay.
And then we get our really tiny scattering. And this is going to be smaller than our wavelength. And so some of it's going to come in, some of it's going to come back, but for the most part, these guys are cruising around no man's land. So we say, let's go here too. So high intensity return. Say mid intensity return, very low intensity return. And then the last part is going to be that Rayleigh, where we have those little red blood cells. And these are much, much smaller than our wavelength. And then this is going to be very low intensity return. And some of it's going through, but a lot of this is just scattering off of these blood cells as we look at that. It's very low intensity.
What do you mean when you say that it is greater than
Fatima, can you send me
So when we looked at that chart, so here's our wavelength, right? So depending on whether we have a high or low, that wavelength's going to change in size. So depending on high or low, we're going to have different sizes of wavelength. But this wavelength, depending on how we're hitting these particular boundaries, the size of our wavelength is going to either be the intensity of it. So it's the, if I have a high frequency, I'm looking at maybe instead of my diffuse being here, my diffuse might be something like this. If I'm looking at a different intensity, my diffuse for that frequency, my diffuse might be something like that. It just depends, and you don't have to know that much about it. You don't have to, nope. Yeah. Just know that it's relative to the wavelength, but they're never going to say, hey, you have a high or low wavelength, or higher, low frequency, what type of, what kind of reflection will we get back? They're not going to ask you that. Good to go so far? Can I erase this?
Yeah.
Do you want to review one more time? You want to break things?
You want to turn it towards the camera? Okay, cool. We got a picture going.
Good to go?
Awesome.
Yeah. Okay. So highest intensity returning beam to lowest intensity returning beam. All right, so we talked about that. Okay, so for our next ones, we're going to have to talk about our angles a little bit. And this is going to be a review for you guys, right? Okay, so we know about obtuse, acute, and right angles, right? So what's an acute angle?
Slow.
Less than 90. What's a right angle?
90.
What's an obtuse angle?
Right away.
There you go. So those ones are easy. We're going to talk about these as they apply to our tissue boundaries. So say I have a tissue boundary here. So we have tissue 1 here, tissue 2 here. So we always compare to what we call normal incidence. So normal incidence is hitting it at 90 degrees. So normal incidence. So we're comparing our beam. Here's our transducer right here. Whoop. We're coming in at 90 degrees to this tissue boundary. So that's our normal incidence. And then we can talk about the angle of reflection. So if I have a beam coming in, so here's my angle of incidence for this particular beam, I. And then I have an angle of reflection. And then this is going to transmit through this tissue. That's going to be my angle of transmission. So we're going to talk about two things about this, and they're very, very different.
What?
Party in the bathroom?
Somebody squatting in the bathroom?
Say it louder.
Okay, so we're going to talk about this kind of whole model as far as transmission and reflection goes. We're going to talk about it two ways. We're going to talk about how we can apply to intensity. We're going to talk about it as far as our angle of transmission. So there's two ways that we can talk about this tissue boundary. One of them intensity, one of them angle of transmission. We'll get more specific about those in a second. So the angle of incidence is whatever angle our beam is hitting this tissue interface. And then we're going to have an angle of reflection. So whatever our beam is bouncing that off of. And then we have some of that beam is going to transmit through that tissue boundary, and that's our angle of transmission. We'll talk about how those angles can change, and then we'll talk about the intensity. Thank you very, very much. Oh, shit. Our hands will be dry from now on. Okay. So, this is just a little bit of backstory. Now we're going to get into the meat and potatoes. Any questions on this so far? So we're just talking about basic terminology, angle of incidence, angle of reflection, angle of transmission.
Sorry, Shea, could you put angles? How do you count them from the baseline?
Yes, we're always counting them from our normal incidence. So from here.
Okay, got it. Thank you.
Okay, so we're going to talk about first about our intensity. When we talk about intensity, we have to know, like, okay, if we go through this tissue boundary, say we're at our 90 degrees here. If I go through this tissue boundary, how much of my beam is going to transmit through, which percentage, and how much is going to reflect back? We call this percent reflected. And we'll get into that in just a second. We call this percent transmitted. So we're talking about intensity here in a second. Yes. Well, we're going to get back to it in a second. This is just your basics. We're going to go crazy on this in a minute. Okay. That reminds me, I need an equation that I don't have in my head. Where is Snell's laws?
Not yet. Okay. I asked to ask her in person.
Yeah. My husband was asking about it yesterday. I'm like, oh yeah, maybe.
Yeah.
Wait, what is that saying? Percent
Percent reflected,
reflected.
percent transmitted. So we're talking about right now, we're just talking about intensity.
Okay.
Is it 100% together or not?
It is.
Okay.
Got it.
I love sitting beside
Thank you.
So we put this tissue boundary. Say we want to know how much is going to be reflected and how much is going to be transmitted. Well, I have an equation for that. And the equation is called, believe it or not, percent reflected. It's the percent of our beam that is reflected back. So, percent reflected. And I'm ashamed to say that I don't have this in my C2 minus Z1. And then it's going to be Z2 minus Z1 over Z2 plus Z1. The whole thing squared and times 100. What are these Z's, you're asking me? Well, let me tell you all about them. They're called rails. Why are they called zales? I have no idea. Whoever made this up, I don't know why they're Z's and they're not. So Z is what's called a rail. And what a rail is is how accepting or not accepting a tissue is to have our beam move through it. And we call that acoustic impedance. How impeding is this? So if I'm out taking a jog, I have very low impedance, right? I'm cruising through, not that I jog, don't pretend that I do. Okay? This is the truth. But I'm jogging. But now I go into a pool and I try jogging, and it slows me down. I have a higher level of impedance, right? Something's holding me back. So we call those rails. And our rails, which is our Z, is calculated by our density times our propagation velocity.
The wheels spelled R-A-Y-L-S?
R-A-Y-L-S. Yep. So they're R-A-Y-L-S.
Like friction moving it back? It's P times
Density times propagation velocity. It's not really friction, but you could think of it that way. But it's more like, how accepting is this tissue to our beam? Remember we talked about density and how, like, if it's more dense, it's slower, our beam moves through it slower. Or if it's less dense, our beam moves through it faster. So it has to do more with that property than it does actually friction. Okay. So we determined that we could have our normal incidence, and we want to say, hey, how much of our beam is going to reflect and how much of it is going to transmit? Well, that's going to be the difference between tissue 1 and tissue 2's rails. So their density and their propagation velocity. Now, you're not really going to have to calculate this, but they're going to say you have an acoustic impedance of this and an acoustic impedance of this. Which one's going to be more reflected? Which one's going to have more transmit? So that's going to be the thing that we're going to ask us. Let's go to our next slide. Okay, so if these have equal Z's, Z1 equals Z2, I'm going to get 100% transmission. So I have to have a difference in acoustic impedances, whether going from low to high or high to low, to have any amount of reflection. So in order to get reflection, we have to have, so for reflection, we have to have Z1 does not equal Z2. Now that doesn't mean one of them's high and one of them's low, or one of them's low here and high here. They just have to be different. The more significant the difference between those, the more reflection we're going to get, regardless of whether we're going from low to high or high to low. So the bigger the difference in those rails, the more reflection we're going to get back. Yes, no, maybe? Maybe. Okay, I'll take a maybe.
So the bigger the difference in rails will be more reflection.
Regardless of whether it's going from high to low or low to high. Yep, the biggest difference. And interesting to note, have you guys tried scanning without gel by accident?
No.
Okay, well, try to look at it. So, if you forget to use gel, you'll notice that there's no transmission. So that's why we use that gel, is to step down the acoustic impedance mismatch between our transducer and the patient's skin and tissues. And so it acts like a little stairway for our move down. And we'll talk about that again later when we talk about coupling agents, not like sexy coupling. So Sean upstairs, he's like, I ordered your lube. I'm like, it's a gel. So to calculate our percent reflected, we're going to take our Z of tissue 2 minus our Z of tissue 1 over our Z of tissue 2 plus our Z of tissue 1. We're going to square that and multiply by 100. They are not going to ask you to calculate this. I think I have one of your class sheets you do, but it's a very simplified version. But for the most part, they're just going to ask you, what does this equation do? It tells you how much is reflected. If I have a significant, like, hey, I have a Z of this and a Z of this, am I going to have a lot of reflection or a little reflection compared to these other Z's? So they're just going to ask you to make comparisons, but you aren't going to have to actually calculate this out. But you will need to know what the equation looks like and why we use it. Something important to note, and this is super duper duper important, it's my last one. This, we can only do percent reflected. It has to be at normal incidence. It has to be at this normal 90 degrees. I cannot calculate the amount reflected or the amount transmitted without being at 90 degrees. If I'm at 91 degrees, 60 degrees, 45 degrees, I cannot predict the amount of intensity that will be reflected and the amount that will be transmitted. I have to be at the normal line in order to make this work. Feeling cool so far?
Mm-hmm.
Okay, so make our little notes over here. So for percent reflected, we have to know our Z's, and we have to be at 90 degrees incidence. So those are the two requirements. So we have to know our rails for each particular tissue, and we have to be at 90 degrees. Those are the two requirements in order for us to use this equation. So let's review that one more time. So we have tissue 1, tissue 2. We have to be at normal incidence. We have tissue 1 and tissue 2. Hey Shea, how much of this intensity is going to go through the tissue and how much is going to reflect? I don't know. What's the difference in
Rails.
rails? So I need to know my Z1 and I need to know my Z2. Now our Z, our rails, is from density times propagation velocity. You won't have to calculate this, you're just going to have to know Z1 is higher or lower, or Z2 is higher and Z1 is lower. You just have to know who's higher or lower and by how far. So they'll say Z1 is 2, Z2 is 4. The next set, Z1 is 50 and Z2 is 1. So which one's going to have more reflection? The second one, right? It's the biggest difference between those.
So the bigger the difference, the more the reflection.
Correct. And it only works at normal incidence, yeah.
But they're gonna give us two differences to compare.
Yes,
and
they'll say, here's this set of tissues rails, here's this set of tissues rails. Which one's going to have the higher reflection or, conversely, the higher transmit?
they won't give us one difference that we then have to plug into the equation. Okay.
Too complicated.
Yeah.
Yeah, too complicated.
Agreed.
Okay, so we have to know the difference in these rails in order to calculate this. So our percent reflected, and again, this only works when?
Okay, 90 degrees.
Yep. So we have to know our rails, we have to know our 90, we have to be at 90 degree incidence. So in this case, percent reflected equals our Z2 minus Z1 over Z2 plus Z1. The whole thing is squared and times 100 because it's a percentage, right? And then how would I get percent transmitted from this number? It's out of 100. So if I get percent, okay, so say my percent reflected is 60%. What's my percent transmitted? 40%. Yeah. So it's just whatever makes up the rest of the 100.
Do we have situation when 100% reflected?
Pardon me?
Do we have any situation when 100% of beams reflected?
Theoretically you could, but we don't have it when scanned. But theoretically, yes.
Yeah.
Yeah. Okay, any questions on this? So this is all related to intensity. So intensity, intensity, intensity. So we can determine intensity at normal incidence, how much is going to go through our tissue boundary, and how much is going to reflect off. Now what happens when these are equal?
No reflection.
No reflection, 100% transmission. You got it. Questions so far? We're getting to my favorite type of attenuation. You know what it is.
And when you refer to intensity, you're saying how intense is our beam, or?
So it's the intensity. So our beam's putting out intensity equals power over area, right? So that's a certain amplitude that's going into this particular space. So the amplitude of my beam going into these tissues, the intensity, the amplitude, how high volume it is. So is it going to transmit all the way through, or is some of it going to reflect back? And so it's the intensity, the volume, the amplitude that we're putting into that patient's body.
If it was 100, then we wouldn't have an image, right? Or
Yeah, correct.
Okay.
Yep. Yeah, you got it. And like we just mentioned, Tanya just mentioned, like theoretically it could happen, but we don't really see it. So. Okay. Any questions on this. So this is just intensity. So what are our 2 requirements for intensity? What do we have to know and have to have?
Rails.
90 degrees? And our rails. We have to know our rails. So 90-degree incidence and our rails. But Shea, what happens when we're not at 90 degrees? Well, let me tell you all that. Okay, we did this. Okay, yes. Okay, we got to do it. Okay, so what happens if our beam's not coming in at 90 degrees? It's coming in at something else. Let's erase this bad boy. So here's our. So here's our 90 degrees. And what happens when our beam, okay, let me start this over. It's coming in at a different angle. So our angle of incidence does not equal 90. Well, then what do we do? Can we determine our intensity?
No.
Why not?
It's not at 90 degrees.
Because we're not at 90, right? But what we can determine is our angle of transmission. Now we're going to talk about, we're going to get intensity out of here. We don't care about you. We already talked about you. We're going to talk about angle of transmission. So tell me about these angles. We had angle of incidence. Who is that?
90.
Whenever we're hitting the tissue at. So 90 is our normal line. So that's like our reference. So angle of incidence is?
You would like us guess 15%.
What is our angle of incidence? What's the definition? It's the angle our beam is hitting those tissues.
Greater than
So
90.
Angle of incidence. So right here, here's our angle of incidence. And then we have angle of reflection. Who's that guy? I hope you know the word reflection. It's the angle that our beam is bouncing back at, right? So let's get this guy out here. So this is our angle I. So here's our angle of reflection. Now this is not drawn to scale because Shea is stupid, but these are always going to be equal. Your angle of incidence is always going to be equal to your angle of reflection. So I put that beam in there at 60 degrees, it's going to bounce off that tissue and leave at 60 degrees. So my angle of incidence, angle of reflection are always going to be equal. Do you know who changes?
Transmission.
Angle of transmission. And he's dependent upon propagation velocity. So for this guy, not at normal incidence, not at 90 degrees. So we have to have oblique. So we have to have an oblique angle. We don't care which one. 91, 89, 100. That's okay, so let's talk about this angle of transmission and how he goes. Oh, Snell's law. Snell's law. Okay, so when we're at oblique incidence, we can't determine intensity because we can only do that with 90-degree incidence. But with our oblique incidence, we can determine our angle of transmission. So angle of transmission. Now, what do we know about our angle of reflection?
It's the same like angle of.
It's the same as our angle of incidence. But this guy can change. So he could be smaller, or he could be much larger. Why does he change? What happened? It's going to be the change in propagation velocities. So we had rails for percent reflected, percent transmitted, and for this we're just going to be looking at the propagation velocity. So C1, C2. So propagation velocity, so we have to have this guy. So for our refraction, we have to have, we're looking at propagation velocity, so C. And then we have to have oblique angle. Now we talked about this angle of transmission either being smaller or larger. How do we determine that, Shea? Snell's law. I don't know who the Snell guy is. He's got a terrible last name. I don't know who this dude is. Okay, Snell's law. Snell's law is, I think it's cosine. Sine transmit sine. So the sine of the angle of transmission over the sine of the angle of incidence equals, well, let's say it's 1 over 2. So propagation velocity 2 over propagation velocity. That's Snell's law. Do we have to calculate this? No. I'm going to give you a real cheap, easy, dirty way to know this. What they'll ask you is, you have a propagation velocity here of 100, and you have a propagation velocity here of 1,000. What would we expect our angle of incidence, our angle of transmission to be compared to our incidence? Higher or lower? Now let me tell you all about it. So, you guys good on this one? Can I erase this bad boy? This is how this works. I'm drawing it. So C1 is greater than C2. C1 is less than C2. I'm going to go down here. C1 equals C2. Okay. Color this one here. So my angle of incidence is coming in here. What's my angle of reflection?
The same.
Same.
Actually, these are going to be equal. Now, if C1 is greater than C2, whoever has the highest propagation velocity gets the larger angle. So in this case, say we're at 60 degrees here. This is going to be maybe 40 degrees. So in this case, our angle of incidence, angle of incidence is going to be greater than our angle of transmit. Just little alligators. Yeah, Connor.
Can you say that first sentence again? Whoever has the higher propagation velocity gets the larger angle between the incident and the transmit. So here we are again. Angle of reflected, angle of incidence, these are going to be equal. Now we'll say this guy's 60 degrees again. And now who's going to get the bigger angle? The guy with the bigger propagation velocity. So angle of transmit. So in this case, our angle of incidence is going to be less than our angle of transmission. Yeah, go ahead. Are you just recording?
I'm recording, sorry.
Okay.
Yeah, thanks.
Okay. What happens when C1 and C2 are equal?
Being past it.
Say this is 60 degrees.
I guess it would be 60.
So then they'll be equal. Oops. So then that way our angle of incidence is going to be equal to our angle of transmission. So whoever has the larger propagation velocity, numeric value, larger propagation velocity, gets the larger angle. And we're making the comparison between the angle of incidence and the transmit angle. So propagation velocity 1 is larger, so my incident angle is going to be larger than my transmit. Propagation velocity 1 is less than propagation velocity 2, so my incident angle is going to be less than my transmit angle. So whoever has the bigger, larger numeric value of propagation velocity gets the larger angle. And we're making the comparison between the incident angle and the transmit angle.
Propagation velocity.
Pardon me?
And then it's just angles.
So these are our angles. So C1 greater than C2, incident angle greater than transmit angle. C1 less than C2, incident angle less than transmit angle. C1 and C2 are equal, incident angle and transmit angle are equal. Can we go over this one more time?
No. Oh,
Yes? Okay.
sorry.
The more confident people can just
You
do
can take a nap back there. Okay.
Sorry.
Okay, so here is our tissue boundary. Here's our normal incidence. So we have
beam is coming in. So it's coming in, we'll say, that looks like a good 45, right? 45 degrees. Or angle of incidence equals 45 degrees. So what's my angle of reflection then?
44.
45 degrees. And we're kind of done worrying about him. We don't care. But now we have this angle of transmission. So if my C1, propagation velocity of tissue 1, equals my propagation velocity of tissue 2, this is just going to be 45 degrees for our angle of transmission. But what if these aren't equal? Well. So if my C1 here is larger than my C2, then my incident angle is going to be larger than my transmit angle. So it might be, we'll say 25 degrees. So propagation velocity higher, larger angle. Propagation velocity lower, smaller angle. Now, if C2 is greater than C1, this transmit angle is going to be greater than 45. So let's say it's 60. Does that make sense? So whoever has the higher propagation velocity gets the larger angle between the incidence and the transmit. We don't care about reflection, he's just going to be whatever incident is. Then he's just kind of hanging out. Trying to be cool, not very cool. Transmit. Yep. Because what's happening here is as we hit this tissue boundary, we're bending that beam. That beam's getting bent. If these are equal, it doesn't get bent at all. But if it slows it down, then it's going to have less of an angle. If it speeds it up, it's going to have a more of an angle. So here's my little, I'm doing 4 wheeling. I don't know what it is. Okay, so we're going in here. And all of a sudden we can go faster. So our wheels come around, and we're going faster, so we have a bigger angle. But now, this is slower. We're getting stuck in the mud a little bit. So as my wheel goes through, I'm stuck, I can't go very far, so my angle is less. By the way, tractors will work like that. Yeah.
So this equation you're saying, it really only depends on the velocity. It doesn't depend on the medium.
Nope.
It doesn't
Propagation
depend
velocity only.
on the tissue, like if it's soft tissue, bone, nothing.
So all of those have their own propagation velocities.
That's true. That's true.
Yeah.
Gotcha.
So,
all right.
So I could say like you're going from soft tissue to bone. So that soft tissue is 1540, bone's like 4,000. Is your
Right.
transmit angle going to be greater or less than your incident angle?
Okay.
Since it's 4,000, it's going to be greater than.
Okay.
Yeah.
So as you pass through different mediums, your angle changes.
And sometimes it comes back to transducer, sometimes it doesn't. And it's just lost in no man's land. Who knows? But that's that bending of the beam. You guys have all probably seen this, like, I don't know if you have like 8th grade science and you put like a pencil in a cup with water and it looks different. Or like you guys, you've all swam, I'm assuming you've been in water before you shower at least. You'll notice like when you see your feet underwater, you like look really short and weird. Or like you're looking at your friend in the water, they look really short and weird because of the bending of the beam. It's not that they like got short and weird in the water and then they like recovered after they got out. Like they just move different because of the bending. Questions? This is my favorite. Might be on maybe a test coming up. This is my favorite form of attenuation.
If half of me was in space and half of me was in the atmosphere, would they look at my legs and see it look weird?
Well, number one,
No, I'm alive.
Okay. Well, I don't know, because I don't know atmospheric bending. Yeah, it would. It actually would. And that's why the sky is blue, is because red refracts out.
Oh, interesting.
Yeah, that's why we have a blue sky instead of yeah, because it refracts out because of the atmosphere.
That's cool.
Now we know. Lights and skies was
Any questions on refraction? So, okay, so let's set up some of these. Let's do it real quick. Okay, so let's go. C1 equals 1,500. C2 equals 12. C1 equals 1,500. C2 equals 200. C3 equals 300. C4 equals 400. C5 equals 500. C6 equals 600. C7 equals 700. C8 equals 800. C9 equals 900. C10 equals 1000. C11 equals 1000. C12 equals 2000. C13 equals 3000. C14 equals 4000. C15 equals 5000. C16 equals 2000. C17 equals 2000. C18 equals 2000. C19 equals 2000. C20 equals 2000. C21 equals 2000. C22 equals 2000. C23 equals 2000. C24 equals 2000. C25 equals 2000. C26 equals 2000. C27 equals 2000. C28 equals 2000. C29 equals 2000. C30 equals 2000. C31 equals 2000. C32 equals 2000. C33 equals 2000. C34 equals 2000. C35 equals 2000. C36 equals 2000. C37 equals 2000. C38 equals 2000. C39 who's going to have the most bend of their beam?
The second.
Second.
The second one. And if I look at, so this is my angle of incidence, this is my angle of transmission, which angle is going to be larger?
The incident.
C1, right? It's bigger. It's a bigger angle. How's that feeling for you? Okay, so we started out by asking which one of these is going to have a greater difference between the transmit and the incident angle. And since these C's are so different, we know we're going to have a lot more difference in the incident and the transmit angle versus these ones that are fairly similar. There's still going to be some refraction that occurs, but not to the significant amount that we're seeing here. And then I said, okay, well now we decided that this one's going to have the most refraction occur. So which one is going to have the larger angle? Is it going to be angle of incidence or is it going to be angle of transmission? So let's use our alligators.
Yay.
Yes, so whoever has the higher propagation velocity gets the larger angle. Okay, any questions on refraction? What is Shea's favorite form of attenuation?
Refraction.
Refraction.
And what are you not supposed to confuse it with?
Reflection.
Reflection and
Rarefaction.
rarefaction. Got it. So as an overview, percent reflected we can calculate at 90-degree incidence, and if we have our rails. Refraction, we can only have oblique incidence, otherwise everything just goes straight through, there's no change in angle. And then we have to know the propagation velocities. Good to go? Okay, we got this. Absorption. So we're going to get back into this again with bioeffects. We talked a little bit about it. So every time we have those rarefactions and compressions occur, we're losing energy, and that energy is lost in our tissues. And so we talked about that kind of thermal changes that we can make to those patient's tissues, bioeffects. More on that next quarter. But we can also lose our beam just to be kind of heat around the tissues, and that's called absorption. So our beam's going in, and we're losing it. It's kind of causing those refractions and compressions, and so we're losing that energy as those particles move, and we're losing it in the form of heat. That can be really bad if we talk about like losing too much of it at once and it cooks the patient's tissues.
Is that friction?
Not really. Well, we'll talk about it again. It's that mechanical and thermal index.
Yeah.
And so it's basically cavitation.
Yeah.
Remember how like when you boil ramen and you get a little bit, it's like the micro streaming, and then the bubbles form, so it's more related to that.
Does friction play a role?
In hemodynamics, it does.
Okay.
Remember like the inertial loss and your frictional loss of blood cells along the wall?
along the wall.
But there's no real friction here because there's not two.
But like the movement of the molecules.
It's related to movement and the
It's not
particle
part of
motion,
the
the oscillation of the particles, but not really like the friction between them. It's more the movement of all of them at once. Does that make sense? But friction we talk about more with hemodynamics because it's actually like
The
we can,
blood cells against the.
yeah, we can actually like numerically evaluate how much inertial loss is occurring because of this level of friction. That's next quarter. Hemodynamics are next quarter. Don't scare yourself. Okay, so now this is proportional to frequency. So the higher the frequency, the more quickly those rarefactions and compressions occur, so the more heat that's going to be lost. Whereas if I have those long, low frequencies, I don't have a lot of rarefactions and compressions happening, so I'm going to lose less heat into the tissues as a group. Good to go? Okay, so then there's a couple constants that we can use. Since we talked about depth, and we also talked about our frequency as being ways to evaluate how much of our beam is lost, how much of our attenuation, how much our intensity is lost, we can do either 1/2 the frequency or 0.5 decibels per centimeter. So we've got another couple equations. So if we evaluate this as being depth related, we can do 0.5 decibels, I should put a D in there, times each centimeter of depth. So I'm going to lose 1/2 decibel of volume, 1/2 decibel of amplitude, 1/2 decibel of my intensity per centimeter. Now Now if I'm starting with 1,000 decibels, that's going to be pretty negligible. If I'm starting with 5, that's going to be pretty significant. Next up, we can evaluate it as it relates to frequency, and that's just our attenuation equals frequency divided by 2. So how much would I expect my 10 megahertz to attenuate? 5 decibels. So 2 different ways. These are not comparable. I can't say at this frequency, scanning at this depth, I have to either evaluate it from a frequency standpoint or from a depth standpoint, but I can't make a comparison between the two. They're 2 separate ways to evaluate attenuation. It's like centimeters and inches. Like, yeah, they're used to do the same thing, but they aren't comparable to each other. Although it is 2.5 centimeters. But they aren't comparable to each other.
Can you repeat this?
Yeah.
Of course I can. Let's use the whiteboard. Okay, so we have 2 ways to evaluate the amount of attenuation that occurs. Frequency, rarefactions, compressions, rarefactions, compressions. So the higher the frequency, the more attenuation is going to occur because of those rarefactions and compressions. So if I have a 10 megahertz, I would expect 5 decibels of attenuation. If I have a 5 megahertz, I'm only going to expect 2.5 decibels of attenuation. So it's half of that frequency. And then we can say the depth thing. So we talked about that left liver lobe going to the right liver lobe and how it got dark at the bottom. We're in there longer. So we're losing 0.5 decibels of intensity, or our amplitude, for every centimeter that we go into that body. So you can see a higher power going in, even if we attenuate, we're still going to be able to penetrate. But a lower power going in, we're going to attenuate and we won't be able to see much at all. Yeah.
Can you tell us when we use decibels? Like for what attenuation? Yeah, exactly.
So,
for volume.
We don't, not really. The way we use decibels is going to be our dynamic range.
Mm-hmm.
It's just a matter of principle. It's just a matter of, okay, our beam attenuates. How much did it attenuate? So it's that constant. It attenuated by 3 decibels. So I'm going to take whatever my initial intensity was, 40 megawatts, and I'm just going to half that. So my initial intensity versus my end intensity is going to be 20 compared to the 40.
So it's related to the amplitude a little bit.
Amplitude, well, amplitude is kind of how we
Power
talk about
to
intensity, right?
Yeah.
Yeah.
Exactly.
Yeah.
So again, you said that I lose 0.5 intensity for every depth.
Yep.
Centimeter depth.
Yep. And then if we look at it by, we're looking at it from a depth perspective,
Yeah.
or we can look at it from a frequency perspective. And how much would this 10 megahertz attenuate? Half of it, so 5 decibels. Yeah.
The second one doesn't seem to tell us as much information.
No, it doesn't. It's more about penetration versus resolution. How come I can't penetrate with a 10 megahertz into the liver? Well, because you've attenuated your beam. You've attenuated 5 decibels, and you only started with 10. So you know what I mean. So you've attenuated half of the beam already. So it's kind of apples and oranges, but we can talk about the loss of amplitude or the attenuation within these 2 ways.
Yeah. Okay.
So you can talk about like how cool Prince is as a musician, or you can talk about how great he dresses.
Yeah.
But we're still talking about Prince, right? Or you know what I mean? Like, same thing. 2 measures for one amazing man.
Symbol.
Yeah, right? Yeah, okay, Prince, all right. Okay, any questions on this business today? So what were our major forms of attenuation? Reflection. Refraction. Absorption. Now within that reflection, there were some subcategories. What did we have? 4 of them. Which is?
Specular.
Spectacularly specular, yes. Specular. Diffuse, which is also called backscatter. And then scattering, and that's special type of scattering. Relay. Got it. Okay, so how are we feeling? Good to go? Okay, so new equations, we've got a couple of those. We have that acoustic impedance, so that's our rails. So our Z's, so what's our acoustic impedance?
Propagation and density.
Propagation velocity times
Density.
density. You got it, that gives us our rails, that's acoustic impedance. Percent reflected. Did you do a bunch of like goofy stuff on that one?
Propagation velocities, difference in the tissue mediums. Percent reflected, difference in rails. But propagation velocity and densities.
That's okay, yeah, okay, all right, you win. But yeah, so that's our rails, and we have to be at 90 degrees incidence.
Yeah.
And then we talk about Snell's law, and Snell's law is dependent upon propagation velocity only
When we're at it.
in our oblique angle. And then we had depth attenuation, which was, how much do I lose per centimeter?
Half a decimal.
Half a decimal, 0.5. And then we had frequency. What's our frequency attenuation coefficient?
Half the frequency.
Half of whatever our frequency is in decimals. Lots of new equations today. You didn't even really know it. Questions?